Hi class. So in our 4.5 video, we are going to be working with simplifying radicals. So again, radicals are the things with this symbol right here. Looks like a check mark with like a roof after it or a ledge after it. So we call that the radical sign, right? Like this, a check mark with a roof. Okay, then the radicals that we have been working with up till now have been radicals that are square roots. But we are going to start looking at higher possible roots indicated by a number written here kind of right where the check mark is, and we call that the index. Now, one comment about that, when there is no index, we understand n to be 2. In other words, we understand it to be a square root, a second root. And then if it's not a square root, so square root is like the default, and then when it's not a square root, we write the number in there for what root it is, and we call that number the index. So over here in number 1, we would say this has an index of 3, and we would think of it as a third root or a cube root. This one here, we would think of the index as 5. So we would think of that as a fifth root. And then here, where there's no index, we understand that that is a square root, or that your index is equal to 2. So simplifying radicals that are either square roots or higher, third roots or fifth roots, we do a similar process that we did when we simplified square roots, but instead of looking for groups of 2, we're looking for groups that are the same size as the index. So you can do this in one of two ways. I kind of do a mashup between the two, but notice how they both start out with factoring. So we kind of want to break up the numbers under the radicals into smaller factors and figure out how many like perfect squares or cubes or whatever the root is, right? Figure out how many of those may already be there so that we can just take the root, or we think of that as simplifying the radical, is when we take the roots of things that are perfect roots, and then things that are not perfect roots would stay in the radical. So I'm going to kind of do a combination of both methods 1 and 2. So in number 4, this one is a square root. The index here is 2 because there is no index. So because of that, we understand the index is 2. So that means I'm looking for perfect squares, if you will. Or you can think of that as groups of 2, right? Whatever the index is, we look for groups of that size because that would make them perfect squares, and then I could square root them. So with 50, I think of 50 as maybe 5 and 10, and then 10 I can break into 5 and 2. So when I'm thinking of 50, it's really 5 times 5 times 2. So I think of that as, okay, I have a group of 2. That means that's a perfect square. I have a perfect square of 5. Therefore, I can square root that and bring a 5 outside of the radical. But the 2 that had only 1, right? In other words, like if you don't have groups of 2, then those aren't perfect squares, and therefore you can't square root them. So they have to kind of stay under the radical sign. So this is sort of like saying the square root of 25, right? Because 5 times 5 is 25. The square root of 25 is 5, and I'm multiplying that by the square root of 2, which is the square root of 2. So this would be our final answer here. For number 5, I have an index of 3. So that means I'm going to be looking for perfect cubes, right? Because this is a cube root, or you can think of that as groups of 3. The index is a size of 3, so I'm looking for groups of 3 because that is, after all, what makes a perfect cube. So I'm going to start factoring 108. I can see that 2 easily goes into the number. So 2 goes into 10 5 times. It goes into 8 4 times. And then I know that 54 can also be divided by 2, and I get 27. Well, there's my perfect cube, right? 27 is a perfect cube, but I'm going to keep factoring. I can break that into 9 and 3, and then 9 can break into 3 and 3. So there's my group of 3, right? So if you're looking at your cube root, I've got 2 times 2 times 3 times 3 times 3, right? Those were the 5 factors that multiplied together to make 108. 2 times 2 times 3 times 3 times 3. So the 2 times 2, even though there's more than one, it is a group of 2, it's not enough to have a perfect cube. You would need a group of 3 to be able to take a perfect cube. So this number right here, that's the 27. I can take the cube root of 27. This would give me 1 cube root of 3 because there were 3. This is not quite enough to take a cube root because I only had 2 of the same factor. So that will have to stay under the radical sign. So I will take out my perfect cube root of 27, which is 3, and then I will multiply that by the cube root of course, 2 times 2 is 4. So that stays under the radical. I just kind of multiply them back together because there wasn't enough to take them out. So I have a 4 under my cube root sign. Why don't you guys try number 6 and 7? All right, so for number 6, you should have gotten 2 on the outside of the square root times the square root of 6. This is because 24 can factor into 3 factors of 2 and 1 factor of 3. So though I have 3 factors of 2, I'm only looking for groups of 2 because the index was 2, right? So I'm looking for square roots or perfect squares. So this right here would be like my perfect square of 4. And then I'm left with a 6. And so the square root of 4 is 2, and then 6 doesn't have 2 identical factors. It has 2 different factors, so they just have to kind of stay under the radical. Now in number 7, it's a 4th root, so we are looking for groups of 4. So 80 can factor into 2 times 2 times 2 times 2 times 5. So 80 happens to have a perfect 4 in it, a perfect power of 4. So because you have this group of 4, you have a perfect power of 4, right? 2 times 2 times 2 times 2 is 16. The 4th root of 16 is just 2. So when you have a group the size that matches your index, you can take the root. You can take the 4th root of this group since you had 4 identical factors. That goes outside of the 4th root and it's a 2. And then we only had a single factor of 5 on the inside, so then that has to stay under our 4th root. Don't forget to write your index, by the way. Because if you forget to write the index, remember we understand that to be a square root, but this is a 4th root. So it's got to be 2 times the 4th root of 5. Moving down to number 8, we see that this is asking us to find the negative square root of 64. So that means that we want only the negative root. Now, it's important for us to note here that the square root of 64, there's actually 2 different square roots of 64, right? There could be either positive 8 or there could be negative 8 because either one of them, if you square them, equals 64. So when we are looking at a square root sign like this one, if there's no negative in front, we didn't really mention this earlier, but we're going to talk about this a little later. But like, for example, in number 4, when there's no sign in front, then we only want the positive root. And that is called the principal root, and is sort of the default, kind of like when there's no index, we want a square root, and if there's no sign, we want only the positive root. But in the event that we do want the negative root, then you will see like a negative sign out in front. So this answer here would have to be negative 8, the negative square root of 64. Now in number 9, we see a plus or minus in front, so that means we want both of the square roots, both the positive and the negative square roots. So we know that 81 breaks into 9 and 9, and of course n squared breaks into n and n. So we actually have a perfect square of both 9 and n, or that is to say we have 2 groups of 2. Groups that match the size of the index. So those are both perfect squares. So when they come out of the square root, there's actually nothing left inside. So this would be an answer with no radical left over, and it would just be plus or minus 9n. Now this one here, so again, there's no index, so we understand it's an index of 2. So remember, we're looking for groups of 2, or we're looking for perfect squares. This is a binomial factor, so remember the x plus 1 has to stay together. I can't split it up. So I'm going to think of it like this. This is the square root of x plus 1 times x plus 1 times x plus 1 times x plus 1, because that's what this power means. It means that you have 4 factors of x plus 1. And again, this is a square root, so we're looking for groups of 2 perfect squares. And again, I have 2 perfect square groups of 2. So again, nothing's going to be left in the radical because everything was a perfect square. And I can take out 2 square roots of x plus 1 from this pair and from this pair. I can basically square root both and take out the root. And these are being multiplied to each other. So the result of this square root would equal x plus 1 times x plus 1. And that is x plus 1 squared. So I want you to notice something here, that the final exponent that I ended up with, this one here, so I ended up with the base x plus 1 squared, that was a result of taking the power of x plus 1 that was originally under the radical sign and dividing it by the index. Because the power is telling you how many factors there are, right? It's the number of factors of x plus 1. It's saying you have 4 of them, right? 1, 2, 3, 4. And then this index is telling you how many should be in each group. So we want groups of 2. So you're basically saying take these 4 factors and divide them into groups of 2. That's division. So you could have found this by doing the power divided by the index. And that could have also been how we arrived at this answer of x plus 1 squared. So I'm going to write that here. So when you're working with variables like this, you can basically divide the power that's in the radical or under the radical by the index. So maybe in some of our future examples coming up, we can kind of use that little trend that we noticed. So in number 11, again, we have a index of 3. So we're going to be looking for groups of 3 or perfect cubes, so to speak. Now 8 is a perfect cube because you can break it into 4 and 2, and then 4 can break into 2 and 2. So this is equal to the cube root of 2 times 2 times 2 times n times n. So for this variable, there were only 2 of them, not enough to make a perfect cube or a group of 3. So both of these n's are going to have to stay under the cube root. So no point in dividing, right? Dividing power by the index, because when I do that, power divided by the index, it's less than 1. That means I can't pull out any n's. They're going to stay under the radical. So we'll just kind of leave them there. But for my number, for 8, I do have a perfect cube of 2, or a group of 3. So I can pull that out of the cube root. So that means I have basically the cube root of 8, if you will, which is 2, times the cube root of the stuff left inside, which was n squared. So that's our final answer for number 11. For number 12, now I'm taking the cube root of a negative, but that's okay, right? This is totally allowed because you can multiply 3 negatives together. In fact, that's what happened here. Negative 5 was multiplied to itself 3 times, right? Because when you do the first 2 negatives, you get positive 25. And then when I multiply that by the third negative 5, my result is negative 125. So because you can multiply 3 negatives together to get a negative, that means you can easily take the cube root of a negative. You just have to be aware that each factor was negative. So that's what we're dealing with here. We've got negative 5 3 times. Now I'm going to write this out the long way and then kind of apply what we learned earlier as well. So there's 9 factors of a, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. That is what the exponent means. This is telling me that there are 9 factors of a. This index is telling me that I want to break them into groups of 3. So you take 9 factors, break them into groups of 3. That's basically 9 divided by 3. 9 divided by 3 leaves me with 3 perfect cubes, perfect cube roots of a. There's also the cube root of, or the perfect cube, I should say, of negative 5. So this is negative 125, the cube root of which is negative 5. This is a to the third, the cube root of which is a, and again that happened 2 more times. So this is another one where there's actually nothing left under the radical sign because everything made a perfect cube. Everything made a perfect group of 3. And so I can take out 1, negative 5, and then 3 factors of a. So that ends up equaling negative 5 times a to the third power. So again, I can see that if you take the power on the inside, which was 9, divide it by the index, which was 3, so that would have given me, so that would have been 9 divided by 3. That'll give you the final power on your variable after you simplify the radical. That's how you can simplify the radical. It's just power divided by index, just like we saw up here in number 10. Divide the power by the index, and that'll give you your final power of your variable after you reduce the radical. So my final answer was -5 times a to the third. So let's try that shortcut here in number 13. So I have an index of 2, because there's no index written. So then according to that rule, this would be x to the power of 2 divided by 2, right? Power divided by index, which is x to the first, which is x. And that would be the square root of x squared. And then for number 14, similarly, I have an index of 4 and a power of 4. So this would just be m to the power of 4 divided by 4, which is equal to m to the first power, or m. And if you think about it, that makes sense, because m times m times m times m, which is what m to the fourth is a perfect group of 4. So you fourth root it, you just end up with m. In 15, again, I can take the base of a. I can think of that as a to the 4 divided by 4, right? Power divided by index, and that would be a to the first. That's being multiplied to n to the power of 8 divided by the index of 4. So I'm taking power, dividing it by index, and so that's a to the first times n squared, or an squared would be our final answer for 15. Now for 16, we have numbers and variables. So for the 32, I'm going to remember that it can break into 5 factors of 2. So first it's 2 and 16, but then 16 is 2 and 8, but then 8 is 2 and 4, and then finally 4 is just 2 and 2. So you see 1, 2, 3, 4, 5 factors of 2. So 32 is a perfect power of 5. So maybe I'll write it out. Maybe I'll write this out the long way, just again to remind you why the division works. So 32 can be broken into 5 factors of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. X to the 5th would be 5 factors of x, and y to the 10th would be 10 factors of y. 1, 2, 3, 4, 5. That's group 1 times 1, 2, 3, 4, 5. That's group 2. I'm just showing you one more long example so you can see why this division works. So this is a 5th root, so we're looking for groups of 5. Perfect powers of 5, which would be 5 identical factors multiplied to each other. So x, it told us here there were 5 factors of x, right? That's what the power means. That's 5 factors of x. There are 10 factors of y. And I want to split that into groups of 5. So I'm basically saying take 10 and divide it by 5. And when you do that, you get 2. So this is another case where there's nothing left in under the radical sign, because everything makes a perfect group of 5 and can be simplified. So the 5th root of 5 2's, or the 5th root of 32, is just 2. The 5th root of 5 x's, or x to the 5th, is x. And then I have 2 perfect 5's of y, so I can take both of them out, and of course we're just multiplying all these things together, right? Because that's multiplied to that and that and that. So this 5th root of all this stuff ends up equaling 2 times x times y, or 2xy squared. Now again, you could also say for the x, right, because it was to the first power, you could take the power of 5 and the index of 5 and just divide them, and that's how we also could have figured out it's x to the first. For the y, you can take the power of 10 and divide by the index of 5 to see that it will reduce down to y squared. So you can use that power divided by index as a shortcut. If you get stuck, you can always just write it out and see how many groups you have that are the size of the index. Why don't you guys try number 17? Okay, so for number 17, you should have ended up with -11 times a to the 3rd power times b to the 1st. It has to be negative because of the negative in front of the root. It wants only the negative root. And then the square root of 121 is 11. And then for the variables, we take the power in which for a was 6 and divided by the index, so 6 over 2 is 3, and then b is 2 divided by 2 as well. Now for number 18 we have an index of 3, so we're looking for groups of 3. But it looks like with the y, if I do the division option where I take the power of 5 and divide by the index of 3, it's not going to equal a whole number. It ends up equaling like a fraction, like it has leftovers. So that means that it's not going to simplify evenly, and there's going to be some factors of y left over. So it might be helpful to write it all out for this one. So for 40, I can split that into 4 and 10. 10 can break into 2 and 5, and 4 can break into 2 and 2. So I basically have 3 2s and a 5. And then I had 3 a's, so that one does break nicely into a group of 3. And then I have 5 y's. 1, 2, 3, 4, 5. So I can see if I'm looking for groups of 3, right, because my index is 3. So I want groups of 3. I have one perfect cube of 2, because that would have been 8. Right? 8 times 5 is 40. One perfect cube of a, instead right here, right? It was a to the third. And I have one perfect cube of y sort of buried in there, right? You can think of this as y cubed times y squared, and that's kind of what this is saying. You have one perfect cube and then 2 out of 3. If I would have just had one more factor of y, I would have had 2 perfect cubes, but I didn't. I was short. So this y squared right here is going to have to stay under the cube root sign. And so is the 5. I only had one factor of 5 that was inside of 40, so the 5 and the y squared will have to stay under the cube root. But I can take out a 2, right? Perfect cube root of 8. I can take out an a, and I can take out one factor of y. Those things can all be on the outside of the cube root. So I get 2ay times the cube root of my leftovers, 5 times y squared. Why don't you guys try number 19? Okay, so hopefully you got x to the third times y squared. We get a 3 for our power of x by dividing 18 by 6, because 6 was our index, and we get a 2 for our power for y by dividing 12 by 6. So here we're using that rule because both 18 and 12 divided evenly by 6, and they were both greater than 6, so they divided into numbers that were greater than 1, so we just went ahead and divided them. And this is our final answer. Now, we've finished walking through the mechanics, so to speak, of simplifying these radicals. But what I haven't mentioned to you yet, and I need to because it's very important, is this idea known as the principal root. There are some rules involved when we are taking or simplifying radicals, especially when those radicals have an even index. And that is, we always want the positive root. So we're going to have to go back and fix some of our answers to make sure that we did that. So how do we fix answers? Well, we use absolute value symbols. So what I'm going to talk to you about right now is when to use those absolute value symbols. Now, the first thing I want to say about that, so put a little star in here. This is only when working with variables. We don't need to worry about using absolute value when we're working with numbers. We can just take the positive root. We just take the positive version of our number answer, no big deal. It's only when we're working with variables that we would actually need absolute value symbols to ensure that we're taking the positive root. Also, it only is required when we have a situation that we call even, odd. This is if you have an even index on your radical, an even power inside your radical, and an odd power as a result after it's been brought outside the radical. This is the trifecta, even, odd. So it looks something like this. We'd have an even index, so it'd be an even number right here that's outside of our radical sign. We'd have a variable, because it only matters when we're dealing with variables, right? If it's a number, we can just take the positive. And that variable would be raised to an even power, so this is even index right here. This is an even power inside the radical, so that's right here. And then when you reduce, when you divide power by index, these two even numbers would divide to be odd. For example, it could maybe be 6 divided by 2, and then I get 3. Or 2 divided by 2, and then I get 1. So it's when you get a situation like this, so my result after simplifying is odd, the exponent is odd, this is when I would need to introduce or insert some absolute value symbols around my final answer. So I just want to talk to you a little bit about why that is the case. Why is it when it's even, odd, I need to insert these absolute value symbols? It has to do with this fact that multiplying an even number of negatives results in a positive. This one fact is what creates this main issue. And let me kind of walk through how it becomes an issue. Well, first of all, we can see that when you multiply an even number of negatives, 2 or 4 negatives, like -3, the negatives cancel each other out and give you a positive result. So we see it here with 2, and then when you have an even number that's larger than 2, if it's even, it can be broken into pairs of 2. And every time you have a pair of 2, those negatives will cancel, giving you a positive, and this will break into pairs, and then those positive results multiply together to give you one final positive result. See, multiplying an odd number of negatives doesn't have that problem. It just results in a negative. So, for example, let's say I had 3 factors of -3. You do -3 times -3 times -3. Yeah, the first 2 will cancel and become +9, but then you'll have like 1 left over. With an odd number, you'd always have 1 left over after all of your pairs are done. So you'd have a +9 times a -3, and then that results ultimately in a -27. So this has an effect on both what you're allowed to plug in and what can come out of an even root, and only an even root. It doesn't affect odd roots, just the even roots. Let's see why. Because let's say you want to take an odd root of -27. That's no problem, right? We just saw a second ago that if I had 3 identical negatives, and in this case -3, and I multiply them together, that gives me a negative. So I can easily find groups of 3, right? Because when you're doing a cube root, you're looking for groups of 3. I can easily find groups of 3 negatives that result in a negative, right? So it's totally possible and not hard at all to take an odd root of a negative. You just get a negative answer. But what about when you're trying to take even roots of negatives, like a square root of -9 or a 4th root of -81? You might think, well, I know the square root of 9 is 3, so then maybe square root of -9 is -3. But then we just saw earlier, well, no, because I'm looking for groups of 2, right? To have a square root, it would have to be a perfect group of 2. So I'd have to multiply the same number to itself. But when I multiply a negative to a negative, it turns positive. So there is no real number that I could multiply to itself that would equal a negative, right? This is going to end up being an imaginary number. And similar with the 4th root of -81. We might think, well, I know that 3 times 3 times 3 times 3 is 81. So I know the 4th root of 81 is 3, so maybe this is -3. But we saw earlier up here, actually no, when I took 4 -3s and multiplied them together, I also got +81, not -81. So that's posing a problem right here, because multiplying an even number of negatives results in a positive. So again, this is an imaginary number. This is not a real number. So when we're working with these things as functions or as expressions, we want to work with values that are only going to result in real numbers. We do not want to work with values that result in imaginary numbers that have the number I. So as a result of that, the domains or the inputs of these even roots must be positive. They have to be restricted to be positive. So we basically avoid taking the square root of -9, and we avoid taking the 4th root of -81. We just don't do it when we're working with real numbers. So when you have functions or equations that look like this, the square root of x, or maybe the 4th root of x, or actually anything of this form, right, an even root of x or x to an odd power, something like this, we automatically sort of restrict the domain so that the variable x would be positive. That's sort of automatically in place in this scenario. And we do this so that all of our outputs will be real numbers. So this is the first effect that this has on even roots, is that the insides need to be positive. Now the other effect is on the output of an even root, the range of an even root, because since multiplying an even number of negatives results in a positive, then when you go backwards to take an even root, there's two possible outputs. There's two possible answers to that, a positive and negative root. So when you get to something like this, right, square root of 9 or 4th root of 81, the question is, which one do I choose, right? The square root of 9, it could be 3 or negative 3, because we know 3 times 3 is 9, and we also know right here, negative 3 times negative 3 is also 9. And same here, 4th root of 81, I don't know, is that 3 or is that negative 3? I'm not sure, big fat question mark, because I know that 3 times 3 times 3 times 3 equals 81, and so does negative 3 times negative 3 times negative 3 times negative 3. So even roots have this dilemma, like which one do I choose? But odd roots don't. The cube root of 27 is just 3, because if I were to take negative 3 times negative 3 times negative 3, I'd get negative 27, not positive 27. So there's no question, this is like easy. And also, I can take an odd root of a negative for the same reason, and I just say, oh, it's negative 3, right? Negative 3 times negative 3 times negative 3 is negative 27. So I know it's either one or the other when I'm working with odd roots. It's either going to have a positive root or a negative root. It's when we're working with even roots that we have this situation of, well, I don't know which one it is. Which one do I choose, positive or negative? So the choice has been decided by this thing called the principal root. The principal root is what we are defining this symbol to be. When you see these radical symbols that are even roots, we understand that those are referring to the principal root, which is the positive root. We are being told to restrict the outcome to be only positive. So what this does is it makes it a little bit easier for us to evaluate these. We know exactly which answer to choose. And it'll become helpful later when we're working with what are called inverse functions. We haven't gotten to that yet, but we will. And in those situations, we want to work with functions that have only one output for each input. We don't want to work with ones that have multiple outputs for each input. So we have restricted also the range of these even roots to be only positive. So now, take for example something like this. I've got my even root, and I'm plugging in a negative, and you might be like, wait, we are restricting the domain to be only positive. But I'm raising it to an even power. So look at this. We square first, right? Order of operations says square first. And so that square, that power of 2, basically turns this into a positive, making it okay for me to have this negative inside the radical, because the square is turning it positive, and then I can easily take the square root of 9 and just say 3. And I know I'm supposed to take only the positive root, so I just take the 3. But what if I didn't know that this was negative 3? And you might be like, how do you not know? It like literally says it right there. Well, what if it was disguised as x? Okay, so I've got a square root of x squared, which doesn't look that menacing, right? It looks fine to me. But what if that x was negative? Well, see, normally when we're taking an even root, we restrict the domain, right? We restrict the domain to make sure it's only positive. But when you put an even power on the x, it's kind of removing that automatic domain restriction. And actually in this scenario, x can be negative now, because this even power right here will turn it positive. We just kind of saw that. But see, I don't know it's negative 3, so I can't just say, oh, negative 3 squared is 9. I can't do that when I don't know what it is. So instead, I simplify it using that property we saw earlier where you take the power and you divide by the index, right? This is an index of 2. So I did take the power of 2 right here, divide it by the index of 2, and I end up with 1. So supposing I did that with my negative 3 to the power of 2 over 2, I'd get negative 3 to the first power. But that's a negative. See, when we're working with numbers, we just know we're supposed to take the positive square root of 9. Oh, that's 3. But when we're working with variables and we don't know exactly what they are, and it could possibly be some kind of negative, like negative 3, for example, we basically put an absolute value around it to make it the positive. So this is the setup that we have to be careful about. It's when you have an even power under an even root. And even more so, if you had an even power under an even root, like we had here, 2 under 2, But then when you divided them, this even power divided by this even root equaled an odd power, right? 2 over 2 is 1. That is when you need your absolute value. Okay, so we know that this is the setup that poses a threat, right? Even index, even power on the inside. So now let's look at this example, because this also poses a threat initially, right? An index of 2, because that's what a square root is, so it's even. I've got my even power, right? So I've got negative 3 to the 4th. X is allowed to be negative here because I raise it to the 4th power first. And that gives me a positive inside the square root, making it okay for x to be negative here. And then we just square root 81 equals 9. No big deal when we're working with numbers, right? But what if we don't know what this number is? And again, you're like, Ms. Lasner, it's negative 3. It's like right in front of your face. But what if it was called x? I didn't know what it was, but maybe x is negative 3 and I just don't know. It's like a negative in disguise. And since I don't know what it is, I can't just raise it to the 4th power and make it 81. I have to instead simplify it this way. I have to take the power of 4, divide it by the index of 2, right? 4 over 2, which is x squared. But look here, if x was really negative 3, right, and I had negative 3 to the power of 4 divided by 2, which is 2, negative 3 squared, would automatically end up being positive. Look, I didn't have to do anything different in this method than I did here. It automatically ended as a positive root or as the principal root. So I don't need absolute value in this scenario if I end with an even power, because that even power, even if my x was negative, like negative 3 for example, the even power would turn it into some kind of positive number. So I don't need absolute value in the case where it ends with an even power. So again, it's only when the resulting power is odd, right? Because we're supposed to have only a positive answer, but this x might be allowed to be negative now because it's being raised to an even power. But if it comes out as x to an odd, that's when you need the absolute value. You don't need to worry about it if the resulting power is even. So let's recap here. Only even roots pose the problem because only multiplying a negative number an even amount of times results in a positive. So it's even roots that have to have a restricted domain, right? Only the inputs can be positive, as well as a restricted range. Only the outputs can be positive. Odd roots don't have that issue. They're exempt from needing absolute value, so we don't worry about it if the root is odd or if the index is odd. Also, we only worry about it if we're working with variables, right? If we know what the number is, we just square it, make it positive, and take the positive root. We don't worry about absolute value when working with numbers, only when working with unknowns, variables. If the variable under the radical is raised to an even power, that is when the domain suddenly opens up to include negatives. That's when we might have a potential output being negative. So we have to watch for the outputs, but only in that case, right? When you have an even power under an even radical, we watch for the output. If the output's raised to an odd power, it could be negative. So that's when we put absolute value around it. That was this example right here. So only when that resulting power is odd do we need to worry. If the output ends up being raised to an even power, we don't have to worry because the even power will turn our output positive already. The example we did earlier when I had negative 3 to the 4th power underneath that square root. When I simplified it, I ended up with negative 3 squared, which already was positive, and that would look something like this. So I would not need to put absolute value around my even power. So only the trifecta, only even radical with an even power underneath resulting in an odd power requires the absolute value. So lastly, what we need to do now is go back through our examples and find the ones that need absolute value. So we're looking for even indexes, even powers under the radical, and then odd resulting powers. So the only ones that even had variables, it doesn't even start till number 9. And number 9 is okay because it had a plus or minus sign in front. So that means I'm allowed to have positive or negative, so it doesn't really apply here. It only applies when we're looking for the principal roots. So number 10 is a possibility because I have an even index and an even power, but it ends even. So it's fine the way it is. It doesn't need absolute value. 11 is an odd index, so I don't worry about it at all. That one's fine as is. It's only if you have an even index. 12 is an even index, so that answer was fine as is. It doesn't need to be changed. But 13, I want you to highlight this one. We're going to have to add absolute value to our answer. This has the trifecta. I've got my even index. I've got my even power inside the index, and it ends odd, right? It looks like this. Even index, x is to an even power, but then on the outside, x is to an odd power. So I need to put that an absolute value. So we're going to add some absolute value signs to our answer. And now it's correct. So make sure you adjust number 13. Number 14, we run into the same situation. We've got the trifecta. We've got the even index, even power, odd result. This one's going to need absolute value. So the final answer is the absolute value of n. In 15, highlight this one as well. We have another similar situation. Not with both of them though, just with one of them. With the a, we had an even index, an even power inside the index, but it ended as an odd. The n squared was fine, but the a needed absolute value. So you only want to put the absolute value around the one that needs it. So it's the absolute value of a times n squared. That should be our final answer to number 15. Now number 16 was an odd index, so we don't even need to worry about this absolute value at all, so our answer was correct as is. Now 17, you might think, oh, well, it says it wants the negative. Right, but only the negative. So if I have my negative in front, then everything that comes after it better be positive. Because if I do, because this is getting multiplied by 11, it's getting multiplied by a to the third, it's getting multiplied by b. If a to the third or b are negative, then that's going to cancel with this negative, making it positive. But I only want the negative. So I noticed that actually both of them need absolute value because they both started off as even powers, right? They were under the even index, and they both ended as odd powers. So because they both need it, you can just put it around both of them. So our final answer would be negative 11 times the absolute value of a cubed times b, which would ensure that my answer stays negative, since that's all I wanted in this case. In 18, I don't have to worry about it because my index was odd, so my answer was fine as is. And in number 19, let's highlight that one. I did have an even index there. So I had even index, and they both actually had even powers. Only the x ends with an odd though, so only the x cubed would need the absolute value. So final answer on that one should be the absolute value of x to the third times y squared. Okay, so when you're doing your classwork, you need to know both the mechanics, how you simplify the radicals, but also when you do and when you don't need to use the absolute value. So it's important to remember even, odd, the trifecta. This is the situation when you would need to use it, and then in every other situation you don't. So this requires a lot of practice. I'm sure you probably will have lots of questions, so I can't wait to see you and help you in class. Bye.